Okay. Yeah, I'll just make sure that at the end of class to load a copy of section 1.4 and 1.5. And let me see, we have a solid 30 minutes remaining. So if we run out of time, I'll release you all, but I'm probably going to stream until I get to the end of this section because I'm using this as my official recordings going forward. Okay. And so you could always watch it at your leisure. So here we're going to be working on section 1.5, factoring polynomials. So with factoring polynomials, what it is remember that example where we did difference of squares and I was like, you can do it in reverse? That's what factoring polynomials is. In the previous section, we were multiplying or expanding polynomials, sometimes using for, and we get these answers. Now in this section, we're going to be starting with those answers and working backwards, right? And that's called factoring. Okay, so 1.5 factoring polynomials. It's just a fancy screen, so I was like, yeah, let's do it. All right, okay. So some objectives here. In this section, you will factor the greatest common factor of a polynomial, factor a trinomial, factor by grouping, factor a perfect square trinomial, factor a difference of squares, factor the sum and difference of cubes, and factor expressions using fractional or negative exponents, right? So factoring is one of those techniques that typically gives students a hard time. They kind of struggle with it. The only way I know to get comfortable with factoring is through practice, exposure, and repetition, right? Practice makes, hopefully you're not saying perfect, right? Practice makes improvement. If practice made perfect, you would never have to practice again. And we all know what happens to our skill level if we stop practicing. If we stop practicing, our skill level goes down. So practice makes improvement. You're either getting better or you're getting worse. It just depends on what you're practicing. Lord knows I practice complaining. So I'm really good at complaining. So I finally made a decision in my mind to be like, you know what? If I'm going to complain so much, I need to do something about it, right? If I can't stop complaining, whenever possible, I need to just take charge and do something about whatever it is that's bothering me, right? So that way I won't. Because I know whatever I'm complaining about, I know it needs attention. And because I see it and nobody else does, I think it's unrealistic to expect somebody else to do it because a lot of times they just won't do it because it doesn't bother them. So I need to take charge and do something about these things, right? Let me see. So once upon a time in the bustling town of Mathopolis, a clever mathematician named Zakaria encountered a challenging problem while designing a community garden. Determined to optimize the garden's layout, Zakaria faced a polynomial puzzle represented the total area of the available space. Using the powerful tool of factoring polynomials, Zakaria broke down the complex expression into simpler factors, unveiling hidden patterns within the mathematical landscape. By identifying common factors, Zakaria efficiently determined the dimensions that would maximize the garden's area, turning the polynomial equation into a practical solution. The garden flourished, and the townspeople marveled at the ingenious use of polynomial factoring that transformed a complex problem into a beautiful and efficient reality. All right. So you definitely can use like factoring to maximize different things. Like if you're like in this case, she was making a garden. You have measurements, and she was able to relate the shape or the size of the garden in a mathematical equation, and she wanted to maximize it so she can produce the highest yield, right? I've used calculations like this, so I do like origami, and there's this like structure, this piece that I would make called the 16 paper box. It's like basically you're making an octagon lid and an octagon base, like the shape of a stop sign. And for whatever reason, I wanted it to be, instead of an octagon, I wanted it to be a hexagon, like a 6-sided figure. And I was trying to get it to fit like this other piece that I had made. So I did some calculations and some rough measurements. And then I made the adjustments based on whatever measurements I had. And lo and behold, it was able to fit, right? So basically I was making like a pencil holder, But it was just interesting. I love like whenever I can see the mathematical concepts that we discuss, and we can breathe life into them. Take them from the abstract as far as numbers and calculations, and apply them and actually use them for practical things. Again, a lot of times it comes out in like construction. It's definitely used in like coding, like all these devices, how we communicate on Teams. You think that they're not using this mathematics to do calculations and send signals and make sure the power wattage is correct, and make sure it's safe as far as radiation, as far as humans are concerned. They're using this kind of stuff, right? I feel like mathematics is like the language of a creator, somebody that's going to build or a producer. And I feel like more often than not, people that make things or produce things, they are a lot of times more successful, right? If you have a product that you sell or a service that you're providing, now people are inclined to give you money, right? But if you're not offering something that's practical, that can help people, they're less inclined to give you money, right? So, So that's just a little observation. I mean, obviously, we're in a different age where things are shifting rapidly and changing, really dynamic. But, it does kind of boil down to what can you offer to others that helps them in some form or way, something they want or something that they need. Let's keep going. So we have the greatest common factor of polynomials is going to be the largest polynomial that divides evenly into the polynomials. So given a polynomial expression, factor out the greatest common factor. So identify the greatest common factor of the coefficients, identify the GCF, the greatest common factor of the variables, combine to find the greatest common factor of the expression, determine what the greatest factor needs to be multiplied by to obtain each term of the expression, write the factored expression as a product of the greatest common factor and the sum of the terms we need to multiply by, right? That's kind of a mouthful. Again, I feel like when you see it in action a few times, it'll sink in. So factoring the greatest common factor, right? Okay, so in the previous slide, it said, first factor the GCF of your coefficients, right? So if we just focus on our coefficients, we have 6, 45, and 21, right? So what I'm going to do, let me think about this. Now, if we look at 6, notice that 6 is what? 2 times 3. So 6 is 2 times 3. 45 is what? 9 times 5. So that's going to be, and I'm going to line up my like factors, but we have 3 times 3 times 5. 9 times 5, right? That's 45. And then 21 is what? 3 times 7. So 3 times, I'm putting my 7 over here because it doesn't line, it's not a like factor with the other guys. Okay. So for my greatest common factor, let me see. Is that the same as the least common multiple? No. Greatest common factor. So the greatest common factor, basically, you ask yourself, oh, well, what's common to all three numbers, right? So they all have a 3, and they all have 1 3. So it looks like 3 is our greatest common factor. Okay. As far as the numbers are concerned. Okay. All right, so we're just going to kind of put a pin in that and move it over to the side. Just going to move it here. Okay. So then if we look at our variables, we have what? X cubed, y cubed. So x cubed, y cubed. So that's going to be x. Let me see. X times x times x times y times y times y, right? We have x squared, y squared, so x squared, y squared. So we have 2 x's and 2 y's. Notice I'm lining up my like factors or like terms or whatever. And then we have x times y, so x times y. Okay, so our greatest common factor, in other words, what's common to them both? To all of them, they all have this x. All right, so I'll highlight that one. I guess we could do it all as blue. They all have at least 1 x and they all have at least 1 y. Okay, so then, so we'll pull an x and we're also going to pull a y. So it looks like our greatest common factor between all the factors, they all have a 3, they all have at least 1 x, and they all have at least 1 y. So my claim is that the greatest common factor between all of these terms is going to be 3xy. Because that's what they all have. Let me see. So first, find the GCF of the expression. The greatest common factor between 6, 45, and 21 is 3. The greatest common factor of x squared, x cubed, x squared, and x is x. Notice that the greatest common factor of a set of expressions in the form of x to the power n will always be the exponent of the lowest degree. And then the greatest common factor of y cubed, y squared, and y is going to be y. And then combine these to find the GCF of the polynomial 3xy. Next, determine, we were supposed to factor. Let me finish factoring. So that's the greatest common factor. So then if we factor that out of all the terms, so this is our GCF. So then the original can be rewritten as 3xy times. Now, from that first term, if we pull out a 3xy, we're going to be left with 2x squared y squared plus. From the second term, if we factor out a 3xy, we have 15xy remaining, right? So plus 15xy. And then from the last term, if we factor out a 3xy, it looks like we're left with just 7. I'm going to shrink this one down as well. Like this, like this. So in fully factored form, we factored out the greatest common factor. And again, yeah, we get this as the final result. So that way, keep in mind, you can check, because if you multiply back, you should get back to the original, right? So 2, 15, and 7, 2, 15, and 7, okay? 2, 15, and 7, okay? So after we found our greatest common factor, next determine what the GCF needs to be multiplied by to obtain each term of the original polynomial, right? So we went back and did this additional step, right? And then we got this as a result. After factoring, we can check our work by multiplying. Use the distributive property to confirm that this equals the original. Okay, we got just under 20 minutes remaining. Let's keep going. So factoring a trinomial with the leading coefficient of 1. A trinomial of this form, x squared plus bx plus c, can be written as the product of two linear binomials, right? Where p times q equals c and p plus q equals b, right? We'll go deeper into that momentarily. Can every trinomial be factored as a product of binomials? Take a moment to just, what do you think? Is that true? Can every trinomial be factored as a product of binomials? I'm going to say, I feel like it's a no, right? Because I could think of some trinomials that cannot be factored, right? So no, some polynomials cannot be factored. These polynomials are said to be prime. So given a trinomial of the form x squared plus bx plus c, again, where the leading coefficient is a 1, list the factors of c, find a p and q, a pair of factors of c with the sum of b, and then write it in the factor form. Okay. So we're asked to factor this. Okay, so let's see this in action. So originally we're given x squared plus 2x minus 15, right? Okay. Now there are some techniques. I think there's like an X method, there's a box method. I'm just going to kind of jump straight into it. If we're starting here, our goal is we want to see, can we factor this trinomial into some form like this? One binomial times another, right? So the first parts are just going to be x's. Now look here. We're looking for two numbers that multiply to give us negative 15 and add to give us 2. Let me say that one more time. We're looking for two numbers that multiply to give us negative 15 and add to give us 2. Now watch this. If we start with the second sign, because the second sign is negative, that means that the two numbers we're looking for, one has to be positive and one has to be negative, right? Because the second sign is negative, that means our signs, one has to be positive, one has to be negative. Because the first sign is positive, that means the larger number is positive. Okay, let's do that one more time. We start with the second sign. Because the second sign is negative, that means our signs, one has to be positive, one has to be negative. Right? Because the first sign is positive, that means the larger number is positive, right? So what is it, 5 and 3? 5 times 3 is 15. And we said the larger number is positive, so the 5 goes here, the 3 goes here. Notice that 5 times negative 3 is negative 15. 5 plus negative 3 is a positive 2. Right? And you can check that this is true. If you FOIL, you should get back to the original. Now, you know you're in completely factored form when you have something times something else, right? Right here. We have something times something else. So that means we're in factored form. Okay? All right, so this is the result we got. I'm just going to put this in a box. And again, you can check if you FOIL out, you should get back to the original. So we got x plus 5 times x minus 3, and you see it there. Okay, let's keep going. Just right at 15 minutes, and we got just about 15 slides remaining. Does the order of the factors matter? Right? For instance, is 2 times 3, is that the same as 3 times 2? Yeah, right? So similar to that, does the order matter? We would say no, because of the commutative property of multiplication, right? So does the order matter? No, multiplication is commutative, so the order of the factors does not matter. So factor by grouping, to factor a trinomial in the form of ax squared plus bx plus c by grouping, we find two numbers with the product of a times c and the sum of b, right? We use these numbers to divide. I'm going to let you read that how-to on your own, and I'm just going to work through an example. So when that leading coefficient is not a 1, now in the previous example, we were looking for two numbers that multiplied to give us c and added to give us b. Well, when that leading coefficient is not a 1, you have to, I call this the AC method. So we're looking for two numbers that multiply to give us a number that's a times c, and then that adds to give us a b, right? So let's see it in action. So in this one, we're asked to factor. We have this 5x squared plus 7x minus 6. Now, the x is to factor by grouping. So the first goal is we want to expand this middle one. We're looking for two numbers that multiply to give us our a times our c and add to give us our b, right? So I'm going to make this one blue, right? So if we say our a times our c, that's going to be 5 times negative 6 is negative 30, all right? So I'm going to write my negative 30 here. And what I'm going to do is list all the factors of negative 30, and I'm going to keep adding those factors together, and I'm going to stop at the line that gives me a positive 7, right? So now 30 is what? 5 times 6. So that's going to be 2 times 3 times 5. Let me clean that up just a bit because that looks like a minus sign. 2 times 3 times 5, right? So I'm going to go through each factor of negative 30, and I'm going to stop at the line that adds up to 7. All right, so the first one is what, 1 and 30? Notice that adds up to 29. So these are not the two numbers we're looking for. We can do 2 here. If we've used this negative 2 already, what's left? Well, what's left over is 15, right? So that's 2 times a negative 15, but this adds up to 13. So these are not the two numbers we're looking for. Let's keep going. Can we do 3? Yeah, we can do 3, right? If we use this 3, what's left over? 10. 2 times 5, right? So we did negative 3 and 10. That adds up to 7. And I think those are the two numbers that we were looking for. Yay! Right? So if we want to do factor by grouping, I'm going to rewrite that 7. I guess let me change that from a blue to purple. I'm going to rewrite that 7 using the two numbers that we just found. And I'm intentionally going to put the 10 next to the 5 because they have a common factor. And I'm going to put the 3 next to the 6 because they have a common factor. Okay. So then the original, we're going to rewrite it as 5x squared. That 7, we're going to rewrite as plus 10x minus 3x. And then that minus 6 persists, right? So all we did, we found those two numbers that equal to a times the c that added up to b. And we rewrote our b using those two numbers that we found, right? So now the factor by grouping, if I group those first two numbers together, what's our greatest common factor out of the first two numbers, right? What can we factor out of those two? It looks like they both have a 5 and they both have x. It looks like we can factor out a 5x from those two terms. Now, if we factor out a 5x, what's left? In the first term, there's an x left over. In the second term, there's a 2 left over. Now, the hint is we're looking for another x plus 2 over here, right? Let's see. If we look at those second two terms, what can we factor out of those two? It looks like they both have -3, right? If we factor out a -3 from the first term, we're left with x. Right? You see the x here. If we factor out -3 from the second term, we're left with the 2. Right? So that's a good omen. So now we have 5x times this blue thing minus 3 times that same blue thing. Right? So each of those terms has a common linear binomial or something in common. What do they have in common? They both have the blue thing. So let's factor out the blue thing from both of them. If we factor out the x plus 2, what's left is 5x minus 3, right? To check, we would say the blue thing times the 5x plus the blue thing times the -3. Then we expand. We should be able to get back to the original. That's how we would check something like this. Or you can FOIL this guy, and you should get back to the original. All right, if you FOIL, you should be able to get back to the original. So what we just experienced is what I like to call the AC method of factoring. Again, to recap, we said our A times our C gave us a -30. We were looking for two numbers that multiplied to give us 30 and added to give us 7. It ended up being a -3 and a 10. We rewrote that 7 using the two numbers that we just found. Remember, I intentionally put the -10 next to the 5 because they had something in common, and I put the -3 next to the 6 because they had something in common. Then we kind of grouped the first two terms together. If they had a common factor of 5x, right? And the second terms, when we grouped them together, they had a common factor of -3. And then each term had a common linear binomial factor of x plus 2. So we factored that out, and we got here, right? That takes practice. Now, there are other techniques. Another technique where we could have done this is called a box method. So if we get something similar, I'll showcase the box technique. Sometimes people use what's called the X method. The X method is similar to the box technique. So if we get another one similar to this, I'll showcase the box method of factoring. And it's similar to this with some augmentations, right? Okay. 5x minus 3 times x plus 2. 5x minus 3 times x plus 2. Okay. All right, let's keep going. So I know we can check our work by FOILing out. Okay, that's fine. So perfect squared trinomials, right? So I think in the previous section, we started with the a plus b squared. We FOIL and we finished with the answer. Now we want to start with those answers and work backwards, right? So if we have something squared, and 2 times that first something times the second something, then we might be working with this guy. All right. So once you can identify it here, you can just jump straight to the answer. Okay, let's see if we can see it in action. So here we're asked to factor, right? So notice the first term, we have something squared here, something squared here. We need to confirm that the middle term is 2 times that first thing times the second thing. Okay? So what's being squared in that first term? It looks like what? 5x. So that first term is 5x squared. The last term looks like what? 2 squared. Okay. So then is the middle term 2 times 5x times 2, right? Well, let's just confirm. 4 times 5 is 20x. That is indeed the case. So then our claim is that it should be 5x plus 2 squared. Okay. Now, if you didn't see that, you could do the AC method like we did in the previous example, and you should get to this conclusion, but it's going to be a whole bunch of extra work. All right. Let's kind of go with this one for now. And again, we would check if we FOIL, we should be able to get back to the original. I'm just going to go with it, just in the interest of time. I see we have, I'm going to kind of keep going. We got a little over 5 minutes together. I might be able to finish this in 5 minutes. So let's just keep going. So difference of squares, this was that special case, right? Before it was introduced to us as a plus b times a minus b, and we got a squared minus b squared. Now we're going to be starting with a squared minus b squared and just work it backwards, right? So once you identify it as a squared minus b squared, you can just jump straight to a plus b times a minus b. Again, when you do these jumps, I cannot stress enough, it's a good idea to check by FOILing to make sure it's correct, right? Because sometimes we remember the property incorrectly, we use the wrong one. So you always want to check by FOILing, right? So, okay, do we have something squared minus something squared? Let me see, it looks like we have 3x squared minus 5 squared. So that is difference of squares, so we can jump straight to a plus b times a minus b. So that's going to be 3x plus 5 times 3x minus 5. Right? And again, you would just check by FOILing. So that's difference of squares. It's a special factoring scenario. Okay. You see it there. Is there a formula to factor the sum of squares? All right. So we saw difference of squares. Is there a formula to factor sum of squares? No, right? We don't. There is nothing for sum of squares. No, a sum of squares cannot be factored. Okay. So, but we do have a sum of cubes and a difference of cubes. Now, I'm going to give a special technique for factoring sum of cubes and difference of cubes. So here we're asked to factor sum of cubes. Now, let me see. We have our x cubed, 512. No, 7, 8. Is that 8? Siri, what's 8 to the power of 3?
I found some web results. I can show them if you ask again from your iPhone.
Hey, Google, what's 8 to the power of 3?
8 to the power of 3 is 512.
Okay, so 512 is 8 to the power of 3, right? So now we have something cubed plus something cubed. So I call this like the chair method for sum of cubes, right? So we have x and 8. We have 3 x's. We have 3 8s. Okay. Actually, let me move this here. So now when we're factoring sum of cubes, first thing is we need two sets of blank parentheses. I like to call them big E smalls, right? We do a small blank parentheses and a big or large blank parentheses, right? Now, because we have plus, that means we're going to do what's called a plus sandwich, right? So we say plus, minus, plus, right? Can you see the plus sandwich? The meat is the minus, and you have a plus on either side. I call that a plus sandwich. If that were a minus, then we would write minus plus plus, right? Another way you can visualize that, because we're given a plus, we're going to put a plus here. The second one is always the opposite, and the last one is always a plus. Let me say that one more time. Because we were given a plus, that's why we have a plus here. The second one is always the opposite. The last one is always a plus, right? So if we had a minus, if we were given a minus, this would be a minus. This would be the opposite, and this is always a plus. Okay. So then from here, let me see. So this is the first part, right? That's just 1, and that goes here. So the x and the 8. This is the second part. All right, put a 2. So x times x gives us x squared. This is the third part. Can you see the chair forming? It's like a cushion or something. So x times 8 is 8x. And I guess we'll go here for the last one. This is the fourth part. 8 times 8 is 64. Can you see the little cushion? You got the back with the seat and the legs. So that's why I call it the chair method, right? So it's a whole little procedure. It's not obvious. You wouldn't know this unless somebody brought it to your attention, right? So, but I call this the chair method for factoring sum of cubes or difference of cubes. Okay. Let me try to do one more and I'll let you guys go. So we saw sum of cubes. This is a showcase of difference of cubes, right? So let's do it real quick. So 8x cubed, I think we're cubing what, 2x? So we have 3 sets of 2x. 125, we have 3 sets of 5. Okay. So if we have 8x cubed minus 125, first we do biggie smalls, so small and then a large. Since we were given a minus, the first one is a minus, the second one is the opposite, the last one is always plus. So that's the minus plus plus, kind of similar to the C++, just the minus plus plus. Okay. Now if we do the chair method, the back is the first part, right? So the 2x goes here and the 5 goes here. The left leg is the second part, right? So 2x times 2x is 4x squared. Okay. The seat is the third part, right? So 5 times 2x is 10x, and the other leg is the final part. 5 times 5 is 25. Come on. Okay, so we saw that one at least twice. I'm just trying to get you all out of here. I see the time. I'm letting you go. Let me see. If you need to go, it's okay. I'm going to go ahead and finish this out because it's only like a couple of slides left. So it's not going to take me that long. I think that's what we got. 4x squared 10x, right? Okay. Just as with the sum of cubes, we will not be able to further factor the trinomial portion. Factor an expression, I think this is the last one. Factor an expression with fractional or negative exponents. We're asked to factor. There's a lot going on there. We could do U substitution. We got a negative power, so that's 1 over that guy. Okay, I'm going to just attempt this one. Hopefully it doesn't take too long. If you need to go, I totally understand. I'm not going to try to get you. But I'm going to go ahead and wrap this up. So that negative exponent causes it to go to the denominator, right? So in that first term, we have this x plus 2. And really what that is the cube root, because I can see that better, right, as a cube root. And then we got this 3x on top. Now this other one, we got this x plus 2. That's in the cube root, and that's a quantity squared, and we have a 4 here, like that. Okay. Now we could multiply by 1. Well, actually, we could get a common denominator. Yeah, let's get a common denominator first. So we can multiply the second one. We can multiply by 1 so that they have the same denominator, right? So I'm going to multiply by 1 in the form of cube root of x plus 2 over cube root of x plus 2, right? So then if we do this, I might have some space here. On top, we're going to have 3x. Now, we already have 2. If we multiply a third one of those, now we're going to have 3, so the radical is going to be gone, right? So then that's going to be plus 4 times x plus 2, right? Let me just kind of reiterate this. Here, we have 2 copies of the same thing, and here's a third copy of that same thing. So then if we have 3 copies of a cube root, they're going to cancel. We're going to have the cube root to the power of 3, so the symbols are going to cancel, and we're just going to be left with x plus 2. Okay? And then on bottom, it looks like we'll have our cube root of x plus 2. Now, this is just how I'm seeing it. We'll see in just a moment the way the book does it. So let me see. We got a 3x plus 4x plus 8 over the cube root of x plus 2. So then it looks like we have 7x plus 8 over cube root of x plus 2. Now, usually we don't leave radicals in the denominator. Again, we would need 2 more copies of the denominator to get a perfect power of 3. So I feel like that's going to make it worse. We might be able to leave it here. Let me just see how they did their final answer. Let me see. They factored out the cube root, so they left it. Okay, so if we want to match ours to theirs, they rewrote it as a negative power. So then this is 7x plus 8 times x plus 2 to the power of a negative 1 by 3. Okay, I think that matches what they have. This one is a little bit trippy. 7x plus 8, and then x plus 2, yeah. So they factored out the term with the lowest value of the exponent. In this case, it's going to be the x plus 2 to the power of negative 3. So in the first term is gone. In the second term, I think they subtracted, right? 2/3 minus 1/3 is a, nope, that didn't do it. What did they do? Because if you multiplied, you would add. So if you divide, you would subtract. Okay. So if you're factoring, you're dividing. So that's going to be 2/3 minus a negative 1/3. So it's a double negative becomes positive. So it turns into a 3, which makes it a perfect power of 3. So that's why the radical's gone. And I think we essentially got that same thing in our second step, right? So it's essentially there. And then they just left it as a negative exponent. They combined their terms and left it there, right? Okay. So we weren't that far off, and we only went over by a few minutes, right? Which isn't too terribly bad. So that one was a little bit, this is going to take some practice. Again, because of examples like that last one, this is why I encourage you all to work together, to collaborate, to link up with a tutor, because stuff like that can be, I know how that can be frustrating, like when you're learning it, but you have to like forge ahead, right? You have to press forward. And again, the confidence and the sense of being comfortable with that information comes from exposure and practice and repetition. Practice does not make perfect, it makes improvement. So the more you practice, the more you're exposed to it, the more comfortable you'll be and the more confident you can be. Are there any burning questions before we go our separate ways? Going once, going twice, forever hold your peace and rights. If there aren't any burning questions, just continue to make your way through your assignments. We successfully made it through 2 sections today, so on Thursday, we just need one more section that we need to do, and then maybe we'll go through some homework together. And that's the main thing. All right. So with that, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your evening and see you Thursday, same time, same place. Take care. Peace.